Hello, my name is Josh Wade. I'm a science fiction fan and your average everyday physics student. As a fan of sci-fi, I spend a lot of time watching movies and reading books based in space. Inevitably, there's an epic battle scene where starships go screeching by, blasters and torpedoes are being fired, and eventually small and large ships are destroyed in huge explosions. I have a question for you. If rebel forces find a way to blow up a space station but nobody is there to hear it, does it make a sound? Let's check out some examples of things blowing up in space. The three examples we're going to look at today are Ad Astra, Avengers Infinity War, and Star Wars. We're going to start with Avengers Infinity War. Thanos just casually killing some civilians. Let's take a look at Star Wars.
Look out! You're all clear, kid. Now let's blow this thing and go home.
The screech of TIE fighters, the roar from the Millennium Falcon, and the deafening sound of an exploding Death Star. Now let's have a quick look at Ad Astra.
Alpha, we have what looks like unidentified rovers approaching our position. Possible pirate activity. Alpha, we need backup ASAP! We're being ambushed!
LRB-2,
Roy!
I have a puncture.
In this scene, the speaking and breathing are very clear, whereas the gunfire and rovers being destroyed are muffled. This leads me to believe that we are hearing the action from the perspective of the protagonist. This highlights the misconception of how sound in space is portrayed. To understand the misconception, we need to understand the physics of sound. The most general definition of sound is a longitudinal wave in a medium. Sound can travel through just about any gas, liquid, or solid. It starts as a vibration by an object. On the left is the simple example of a drum, and the membrane vibrates and it moves the air around it in and out. Those moving particles make the air move around them, creating a chain reaction that makes the sound spread outward in a wave. When these particles move back and forth in the air, they end up bunching together at some points and spreading out at other points. This bunching and spreading creates pressure differences. How often these pressure differences occur is called frequency. We detect frequency as pitch. Higher frequency makes a higher pitch. A lower frequency makes a lower pitch. You may ask how we know that sound requires a medium to travel, and there is one piece of compelling evidence that it requires a medium, the speed. Since the speed is different depending on what the sound wave is traveling through, the speed of sound is dependent on the properties of the medium. The more tightly packed the molecules of the medium are, the quicker they can interact with one another, and that moves the wave along faster. Okay, sound travels at different speeds, but how do you know it happens in a wave? Two reasons. The first reason is the Doppler effect. When a sound source is moving, the waves in front of the source bunch together, and the waves in the back spread apart. It's the old traveling siren example. The pitch is higher as it approaches, and lower as it drives away. The second example of how we know sound travels in waves is interference. When two waves occur in the same space, they can interact with one another. For example, when two tuning forks with slightly different frequencies are sounded together, or when two organ pipes that are supposed to have exactly the same frequency are slightly out of tune, they create a beat. This beat happens as the waves travel in and out of phase, as demonstrated in the diagram. Speaking of pitch, it's important to discuss how we detect sound. In a sinusoidal sound wave in air, the pressure fluctuates above and below atmospheric pressure with the same frequency as the motions of those air particles. These pressure differences create vibrations in the eardrum. The eardrum vibrates small bones behind it that in turn vibrates the cochlea, and from there on this becomes more of a lesson in anatomy than physics. So this process is why your voice sounds different when you're speaking than when you're listening to a recording of yourself. When you're listening to a recording, the sound waves are traveling through the actual air and vibrating the eardrum at a frequency created by the properties of air. When you're speaking, the sound waves are traveling through your body, and the properties of your body as a medium create a different frequency than that of the air. So, to answer the question posed earlier about exploding space stations, the answer is no, regardless of the presence of a person there to hear it. The reason for this is that space is a vacuum. This means there's no matter in space. Without matter, there is no medium for the sound wave to displace so that it can travel to our ears and create the necessary pressure differences to vibrate our eardrum. So sound can't travel in space. To an observer watching a space battle, the battle would be silent, not filled with gunfire and explosions. In conclusion, the entertainment industry either doesn't understand the physics of sound or ignoring the physics because silent explosions aren't terribly entertaining. In fact, in The Expanse, the author of the book goes to some length to explain how sound does not travel in space and illustrates a scenario where characters would press their helmets together to transmit the vibrations from one person to the other. In the show, however, they portray the roar of the engines and the big explosions. As a sci-fi fan, I can get past it, but you'll never hear an explosion in space. Thanks for listening. Have a good one.